So we have seen the average waiting time, that is, it is 17 for these processes P1, P2 and P3. And for the average completion time, when it actually leaves the CPU, it is 27. When the process arrives at P1 first, then P2 and the P3. This is the sequence: P1, P2 and P3. Now let's see, what if their order had been, that means, what if the order P2 first, then P3, then P1? See, the burst time is same. That means the CPU time for each process is same. That means the P1 CPU time is 24, P2 is 3. See, it is same. It is same. But the order of arrival is changed now. What it is now? It is P2, then P3, then P1 at any point of time. Maybe it is 0, it is 1, it is 2, maybe it is 0, 1, 2 at any point of time. But the order of the sequence of the arrival is different now. It is P2, P3 and P1. Now see the average waiting time and the completion time. See, P2 came first with a burst time 3. Now for the next 3 seconds the CPU will be given to the P2 now. See, next P3 came, burst time is same 3. For the next 3 seconds from 3 to 6 it is given to P3. Same. Now for the next 24 seconds, because at last P1 came with the burst time 24, it is 6 to 20, 30. Right? Now see, let's compare these values. The waiting time earlier for P1 is, see, it is 0. Now it is 6. See this, it is arrived at this time, right? Now for the waiting time, P2 is 3, and it is, wait, just put this value. It is P1, it is 6. For P3 it is 3. For P2 it is 0. Clear hai? Because P1 arrived at last and waited from 0 to 6. The time for waiting time for P1 is 6. Now P3 arrived at 0 and waited for 3 seconds. The waiting time for the P3 is 3. And P2 arrived at time 0 and get the CPU. So for, let's see here, waiting time. See, for P1 it is 6. For P3 it is 3, and for P2 it is 0. Now compute the average waiting time. That means sum of all this, it is 0 plus 6 plus 3 divided by 3. See, in the last, when they arrived in the order of P1, P2 and P3, the waiting time is 17. And this time it is 3. See the difference. It is more than the 3 times of the current waiting time. See, अगर मैं देखूं तो 3 into 5 equals to 15. It is 17. Just by changing the order, we have seen the difference between the waiting time. Right? Now see in the average completion time. P2 completed at time 3. See, P2, let's see the completion time or the exit time. This is also called as the exit time. Now, P2 completes at time 3, P3 at 6, P1 at 30. Right? Now, calculate the average of completion time. That means sum of all this, 3 plus 6 plus 30 divided by 3, it is 13. Earlier it was 27, now it is 13. The difference closely double or almost half. This time it is half, closely half, right? So if just by changing the order of the processes, we can see the difference between the waiting time and the completion time. It's the average waiting time and average completion time. Now, average waiting time, it is 3 to 17. Just by changing the order, it is 3 to 27. Now see the pros and cons. That means what are the positive points or advantages of a FCFS and what are the negative points of FCFS. See, short job gets stuck between the long job, as we have seen in the first example. The first example we have seen this. Let's see the quick see. P1 with the longest burst time, that is 24, came first, and the most shortest burst time, that is process P3 with the 3, process P3 with the 3 and P2 with the 3, had to wait 24 and 27. This is the longest waiting time for these processes. So this is called as basically a starvation. That means shortest job get stuck behind the long ones, right? If any job came with the burst time, suppose it is 25, maybe 30, and the process with the burst time 3, 4, they can just complete their processing in just 3 seconds, 4 seconds or milliseconds, but they had to wait by 25 and 30 seconds just by the order of the processes, because they came late. So the shortest job get stuck behind the long ones. Like suppose you are in the queue and waiting for their time to fill their bottles. Suppose a person with 10 bottles came first. It is a tap, water tap. Suppose the scenario of hostel, where we all live in a hostel once in a life. See, there's a tap, and a boy with 10 bottles came first, and a boy with 1 bottle came last or second. That means that just by us, he has to fill a single bottle, but he has to wait till this person fills their 10 bottles, right? So this is the problem. Performance is highly dependent on their order in which the jobs arrive. Obviously, we have just seen the waiting time, which was 3 and 17, right? Completion time, which was 13 and 27, I guess, right? The difference, it is 3 times, 2 times. These are some performance criteria for the algorithm. Now, we will see how we can improve this. Just see the improvement of FCFS. इसका improvement क्या हो सकता है? How we can improve this? मतलब improvement of FCFS. First come first serve. It could be, as we have seen, it is a non-preemptive in nature. It is always non-preemptive, right? What if I make it preemptive? Then the preemption came to the picture now with some time slice. 2, 4, 5 and so on. That means that suppose it is time slice 2. For the current 2 seconds, the CPU goes to the J1, then job 2, then 3, again J1. Okay, right? So here all the jobs or the CPU is in the preemptive mode, and the time slice 2 seconds. Then that means after 2 seconds, job J1 have to leave the CPU at any cost, just to give chance to the CPU or job J2. Now, after 2 seconds, job J2 also have to leave the CPU just to give chance to the job J3. Maybe job J1 has a burst time 24, but job J2 has a burst time 2 only. So it would not have to wait for next 24 seconds. It will complete in the next slot only. See the scenario? Let's see this example. Now, round robin, hour scheduling. This is the improvement of FCFS, right? That means it is good for short jobs. Suppose job time, burst time is just 2 seconds, 4 seconds, 5 seconds, 3 seconds. It is good. But when a job with a burst time, longer burst time, suppose it is 24, 30, maybe more, came for the CPU, and at first, then the shorter job have to suffer. So it is good for short jobs, but not for the longer jobs, right? Depends on submit of order, key when they're arriving. If you are first in the market list to buy the milk with some small packets, then it is good for you. But you have to, if you have to buy 10 packets, yeah, only one packet, and then the person with the 10 packets came first, or maybe after 10 packets the market is out of stock, then you have to suffer. So this is the case of the Fcfs only. Now see the round robin. Each process gets a small unit of time quantum, or a time slice. Okay, right? So each process will get the CPU for some time quantum or a time slice. Let's say it is usually it is 10 to 100 milliseconds, maybe 10, maybe 100. It is too short. It is in milliseconds, right? After the quantum expires, the process is preemptive. That means it has to leave the CPU and add it to the ready queue. That means suppose it is a ready queue. So this is the CPU with the job J1. It is preempted. Now it will come to the here job J1. Now job J2 will get the chance. This is the ready queue. Right. After quantum expires, the process is preempted and added to the ready queue. Suppose we have n processes, n value some maybe 5 processes we have in the ready queue. It is job J1, 4, 3, 5, right? And time quantum is q seconds, some seconds, 10 seconds, 20, 30, 40, some seconds, right? So we have n processes with some time quantum q seconds. Each process gets a 1 by n of the CPU time. It is clear. Suppose there are 5 processes, so the CPU will divide into the 5 times. 1, 2, 3, 4, 5. It is this time is 1 by 5. If it is n, it is 1 by n, right? In chunks of at most q milliseconds. What is the chunk? Chunk means this particular time. This chunk, these are the chunks. Time slice, time quantum. So it could be the maximum q second. That is the given in the question only. What is the time quantum for this round robin scheduling? If it is time slice is 2 seconds, so this is maximum 2 seconds. If it is 4, maximum 4 seconds, and so on. What is the maximum waiting time for each processes? We will see. See. Performance of this particular round robin scheduling depends on the size of a queue. That means here in the round robin scheduling, the main hero of the scheduling is queue, time quantum, time slice. Okay. जितना छोटा रहेगा, smaller the queue, it is interleaved. That means more context switching. Between the processes. Every time J1 coming, with J2 coming, J3 coming, their PC should be loaded in the main memory, then in the secondary memory, then main memory, secondary memory, and so on. This is the context switching. The smaller the CPU time, smaller the queue, it is more time context switching. Clear. Large queue is like, it is more like Fcfs only. See, queue must be large with respect to the context switch time. If we want to minimize this overhead, that is, what is the overhead here? Context switching. We must take care about the queue, that it should be maximum, more. Otherwise, overhead is too high. That means context switching time is too high. Changing. then J1, 2, 3. That means the CPU will spend more in the context switching time. It's spending most of the time in the context switching. Right. So these are the scenarios when the queue is small, when the queue is large. Here's example. Example of round robin with time quantum 4 units, some unit, maybe second, millisecond. It could be anything. And the process P1, P2, P3 with a burst time 24. Same example, 3 seconds. This is the CPU time also, CPU time. Right. Now, see the Gantt chart for this. This is also the order of these processes. Right. But that means P1 arrived first, then P2, then P3. Right. At time 0, all 3 arrived. That means P2 is also here, P3 is also here. But P1 arrived first, it will get the CPU. But not for the next 24 seconds, because since it is a round robin scheduling and the time quantum is 4 seconds, only for the next 4 seconds. See. Next, P2 it is in the ready queue and the top. P2 will get the CPU, but not for the 4 seconds, because the burst time for P2 is 3 seconds only. So for the next 3 seconds, P2 will get the CPU. Right. Next, P3. P3 will not get the CPU for 4 seconds, because the burst time for P3 is 3 seconds only. So for the next 3 seconds, it is P3. Now, there is no one in the ready queue, only P1. Just switching, same, 14, 18. That means after every 4 seconds, it waits if any new process is arrived. Maybe any other process P4 is arrived, P5 is arrived. So that means after 4 seconds, it is checking if any other process arrived. Right? Since there is no one, so the process P1 is in the CPU only till it completes its processing. Now, see the waiting time. See, this is the Gantt chart. Right. Now, calculate the waiting time. How we can calculate the waiting time? See, it is waiting time for P2 is P2 arrived at 0 but get the CPU at 4. So it actually waits from 0 to 4. It is 4. Clear hai? Now, calculate the waiting time for P3. It arrived at 0 but waits till 7. It is 7. Right? Now, calculate the waiting time for P1. It arrived at 0 and get the CPU. There is no waiting time till here. But at time 4, P2 is allocated to the CPU. At 7, P3 is allocated to the CPU. That means from 4 to 7, it actually waits for the CPU. That means it should be added in the waiting time of the P1. That means it is 4 initially. Next, 10 minus 4. It is totally 6. It actually waits in the ready queue for the CPU for the 6 seconds from here to here. See, that is. Now, see the completion time. Clearly, for the completion time for the P1, it is 30 when it leaves the CPU. Right. Now, for the P3, it is 10. And for P2, it is 7. Right. Now calculate the average waiting time. Sum of all this. 6 plus 4 plus 7 divided by 3. It is 5.67. Average completion time. It is 37.10. Sum of all this divided by 3. It is 15.67. This is the average waiting time. 5.67. Average completion time, it is 15.67. In the round robin scheduling with the time quantum 4. Problem is same. Now, let's say the turnaround time varies with the time quantum. Turnaround time is it actually the time the sum of the time it waits in the waiting queue plus burst time, right? When it is arrived here and waits for the CPU, is the waiting time, we know that. And when it gets the CPU and completes its processing, it is the burst time. Or we can say exit time, it is exit time minus arrival time, AT. This is the turnaround time. See, now for the time quantum from 1 to 7, this is the graph between the time quantum with the average turnaround time. It is 11 to 11.5, then some minus 11, then 5, 11.5, then 12 point something, then minus 10.5. This is